Welcome back, friends, to the online training course on Google Earth Engine and its application to water resources. This is the third session of my part. First, we have covered the bathymetry survey methodologies, then satellite-derived bathymetry techniques, and the data analysis procedure. In the second session, we have discussed about the software process by which we can extract the boundary file using Surfer, how to analyze the data, gridding procedures, then making the data to extract the bathymetry, and then make a map for the satellite derived bathymetry so that multiple reservoirs in one scenery could be bathymetry could be extracted. Now in this session we will touch upon the water quality aspects of it. With the same Google Earth Engine platform and with using Python, we will see how the water quality is estimated, and we will have the practical part followed by this. Okay. So again, I thank the team who are part of these studies. The basic concept behind the water quality estimation is the multispectral data has a different reflectance with reference to the material content of the water. So in case this particular slide is acceptable, then the technology what we are going through further will be very simple to understand. Now every band will have a different absorption coefficient. So similar to the bathymetry extraction, the direct relation with the band is 1, and with reference to different ratios are also another one. So if you could able to get the proper mathematical relation or the best mathematical relation by multiple regression methods, then we will able to get a good correlation. And then those particular bands can be utilized in extracting the water quality indexes such as dissolved organic matters, suspended solids, polyorganines, chlorophylls, and every other portion. So this is being taken by my other colleague also in a separate session. So we will see how the water quality based on the color component are extracted by training this information by putting them into classes and defining them into classes and then training through a neural network based approach. So in this practical portion, we will be showing you this process, how it is been done. So here again we used Google Colab. And we have and the process of data creation. It involves data collected from a laboratory experiment, from the Google open source, and also from the field data. Now from the collected data, we have created 6 classes of color for the machine to learn. Then the associated libraries to for the neural network to learn the 6 classes and then map it. Then we have to tune the model for different conditions, which has been taught to the machine for its learning purpose. Then once the model learns and it is trained, then we will see how closer it is predicting the results, and which we will be showing you live with the session which is going to continue along with that. So here you will appreciate the role of artificial intelligence, which is in a generic term. So within which we have a machine intelligence. Machine intelligence comes not on its own. We have to teach it. I think some of the portions I have already explained the learning methodologies in my first session, and then with when the complexity, now in the present case we have worked in a normal machine learning with the neural network approach. In case if the complexity increases or if you go further down, narrow down our classification or the search algorithm, then we will be going to a deep learning concept where you will have multiple hidden layers. The machine will be taught with multiple layers of neurons. So with this we will now go to the hands-on session, where again we used Google Colab, QGIS, and with the neural learning approaches. So thank you.
Welcome back. Now we will be looking into the water quality code in more detail. So there are three parts or two parts basically to this code. The first one is the backend where the neural network is trained and visualized. In the second part, it is called as the front end where the trained neural network is saved and called back to perform predictions on new images. So first we will look into the backend. So the backend part begins firstly by importing the required libraries. The first library we have imported is NumPy. NumPy is very useful for multidimensional array manipulation calculation. As we all know, images are in the form of a matrix which are further converted into an array. So over there, NumPy is greatly used. After that, we have imported Matplotlib. In that, PyPlot, which is a very famous library to visualize heavy data, images, and other things. So basically, it is used for visualization of the data. TensorFlow is a machine learning library where it has lots of machine learning modules which we can use accordingly to the data. After that, Keras we have imported. Keras is also a machine learning library, and TensorFlow and Keras we can say walk hand in hand. After that, in that we have imported layers which are our neural network layers, and in that also we have imported a model which is sequential. The word sequential tells or defines itself as one after the other. After that, we have provided the path of our data which is in the cloud in Google Drive. So over here data directory is nothing but the path of the data. After that, we have divided our data set, the total data set, into batches. So each batch will be consisting of 32 images, and each image will be having height and width of 180. After that, we have trained, or before training, we have splitted our data into training and validation. So in this part, we have considered 80-20 split, and assigning batches to the images, assigning the height and the width also. So over here you can see it says that found 850 files belonging to 6 classes. So in all there are 6 classes which are um, black, blue, brown, green, red, and white. That means any water body image we will pass to the code, it will give the output in format of like this image belongs to the black class or blue class. If the image is of green color or the water is of green color, our neural network will predict it as green water body. In these folders, this is the total data or the data directory in which we have around total 850 images divided into 6 classes, out of which we will be using 638, which is around 80% of the data for training, and 212 images, which is around 20% for validation. Not 20% actually. Then after that, we will be defining the class names. The system or the machine understands only the language of zeros and ones. So we are telling that if the output is 0, we need it as black. If the output is 1, we need it as blue, then 2 brown, then 3 green, and so on. Otherwise, if we don't put this statement, the output will be the given image belongs to one first class or 0th class or 5th class, and accordingly. After that, we have performed auto tuning, in that we have shuffled the data set, and in the next part we have performed or we have tried to create randomness in the data, where we flip the image into horizontal by the horizontal axis. We adjust or we change the contrast of the image. Then we provide random rotation, or we do random rotation on the image. Also we do random zoom. So not necessarily always an image will be taken in a particular angle. So we need to train our neural network accordingly by generating randomness. After that, we have defined the model. As I told you, it is a sequential model, and the total number of classes are 6. In that, first we will be creating or rescaling our data set. That means normalizing. That means each and every pixel intensity value will be between 0 to 1. Previously it will be into the range of 0 to 255 multiplied by 3 channels. After that, it will be in the, after rescaling, it will be in the range of 0 to 1. As we can say, this is normalization. After that, there is a convolutional layer. It is basic convolutional mathematics in this, of the size 16 by 3, and we are using activation layer, which is ReLU. Basically, activation layer we can say are as a switch, that if the certain parameters are seen, then only it will turn on or it will be in the off state. After that, there is a max pooling layer, which selects the maximum value in that particular array, and then basically it scales down the input image. After that, we have again used a convolution layer of size 32 by, or we can say 32 kernels of size 3 by 3. Kernel basically is a matrix. After that, we have again introduced max pooling layer to again downsample the image. Then again convolutional layer. Over here, all of the activation layers are ReLU. After that, we have used a dropout layer, which is used where the model seems to be overfitting in the sense it overperforms. After that, we have used a layer called as flatten, which convert all the data, multi-dimensional data, into a 1D array, into a single dimensional array. After that, a dense layer of 128 is used. A dense layer is basically a fully connected network where each and every, we can say, a neuron is connected with each other. After that, we have defined the number of classes, which are as the last layer, which we have already provided, is 6. After that, we have compiled, and over here in compilation, we have used the optimizer as Adam, and in loss, to calculate the loss of the model, we have used sparse categorical cross entropy, and we are going to be observing the accuracy of this model while training. So basically, optimizer is to reduce the error while predicting or while training, and loss is basically, like for example, the more the loss, the poor performing model can be defined. So we need the loss as least as possible. After that, we will be going to the model summary. So it is a sequential model, then first it is rescaling, afterwards there is a convolutional layer, max pooling, and so on. After that, we will be training our model into 20 epochs. Epochs means number of repetitions. After that, as you can see over here, the loss is reducing. which is good, and the accuracy is increasing. This is for training, and for validation also, loss is reducing and accuracy is increasing. As you can see in the last epoch, the training loss and accuracy are as 0.13 and 0.95. That means 95% accuracy. And for loss, it is 0.48 loss, and validation accuracy is 0.87. That means 87% accuracy. So we have calculated an average accuracy and also visualize the training and validation process. So these are the graph which represent the training and validation accuracy and training and validation loss. So as you can see, with the increasing number of epochs, the training and validation are almost walking hand in hand, and also loss, while training it is reducing, but while validation the loss is much volatile, which is actually bad for this. So now our training and validation accuracy average are around 88.64 and 88.27% respectively, with losses of 0.31 and 0.36. In the next part, we have, after finally or successfully training the neural network with appreciable accuracy and least loss, we will save this model by creating first a directory in which we will be saving this model, and again load that model to perform predictions on new images. After that, we have, as I told you previously, we provide class names, or else our output will be in the form of 0, 1, 2, 3, 4, 5, depending on the number of classes. In the next part, we have performed prediction, where we pass the image or provide the path of the image, convert it into the array, and call the prediction function, pass that array, and predict the image. Alongside, we have given an opportunity or the part where few experts in this domain will be able to add, for example, when the watercolor is black, what might be present in that water, for example, black ink and few components which provide black color to the water. So the final output looks like this. This image most likely belongs to red with 100% confidence. It might contain traces of rust. If we, in this part, in the if else part, if we add along with the rust, we say copper traces or whatever, which will give red color to the water body, that will be printed alongside. So this is basically backend, where the model is trained, analyzed, and saved. In the next part, which is front end, we simply import the required libraries, import the model, saved model, which we don't have to train it again. In backend, if we run this whole code, it will take appreciable amount of time, hours maybe, depending on the system. That's why I will be not running this right now, but we will be running and seeing this front end part. So firstly, I will just mount my Google Drive. So once my Google Drive is mounted, the reason it is asking for authorization is this code is actually shared. So it will ask the main author for the authorization. After that, we will be importing the required libraries: NumPy for multidimensional array calculations and manipulation, Matplotlib for visualization, TensorFlow for, it is a machine learning library, PIL, that means pillow, to visualize the images, and Globe for file management and everything. So after that, I will be running this part where I'm providing my directory path, my model path, then the images which I will be passing to this model, the new images, real world images in sample directory, and class names which are black, blue, brown, etc. After that, I will be passing each single image, converting into the array, and then performing prediction on that. And I will be plotting those images sequentially. Along with this if else statement, for example, if my prediction is blue, then it will, along with the blue, it will print that it might contain traces of copper sulfate. For brown, it might say mud, rust, tannins, suspended sediments. We can also increase the number of parts by simply putting commas and adding things to the list. So these are few internet images. I will like to show you real world images which are as follows. So over here the model has predicted this is most likely a blackwater image with 99.70% confidence, and it also says that it might contain traces of water softeners, sulfides, manganese, clay, cement, etc. After that, you can see this image is of a green water body where it has predicted it is most likely a green water image with 65% confidence, and also it has said that it might contain traces of algae, phytoplankton, chlorine, etc. These are few satellite images. So over here it says that it is a green water image. Over here it is said as the red water image. Similarly brown, then green, and these are also the real world images of canal where it has predicted that it is a black water image. Some few parts where the light intensity is changing, it has predicted as white water. So basically in real world we have achieved an accuracy around 70 to 80%. So this is also wrongly predicted as brown water image. It should be black. Over here also you can see it is a clear water or white water image, but it has predicted black water. But over here it has predicted that it is white water image with 90% confidence, and it might contain traces of sodium carbonates, bicarbonates, etc. We can also use this by passing drone images. So similarly in this part also I have just imported the required libraries, mounted my Google Drive, provided the path of the saved model and the directories, and this part is for prediction. So we have these are few internet downloaded drone images. Here also it has predicted very good at some parts. For example, this image, this is most likely a black water image, but actually it is a brownish blue image. Over here it is a green water body, so it has the angle not necessarily should be a specific angle. So these are aerial views. These are taken like from a land view. So this is most likely a green water image, and this is also taken from a mobile phone. It has predicted that this is most likely a brown water image. So this was all about the water quality part. Along with this, by doing classifications for not only color, we can do what like for example oxygen concentration, then carbon concentration, nitrogen concentration, and everything by just using satellite images like we did for depth estimation. Thank you.